I believe everybody has gotten their lunch and is sitting down now, so in the interest of time, we're going to go ahead and start with our next speaker, our luncheon speaker, who's Dr. Paul Spudis. Dr. Spudis received his undergraduate degree in geology at Arizona State back in 1976, received his master's degree in geology at Brown University in 1977, and got his PhD back at Arizona State University in 1982. And since that time, he's been doing research in planetary geological processes, and has served as a principal investigator for many lunar and planetary experiments, and is currently at the Lunar and Planetary Institute here in Houston. I had the pleasure of working with Paul on the synthesis group back in 1990 when we were looking at going back to the moon and Mars. So I think he has a background and a great background in understanding of the moon and what benefits that we would really gain from going back to the moon. So let me turn it over to Paul.
Thank you, George. I'd like to speak to you for just a few minutes on some work that I and many of my colleagues have been doing over the last few years. We have found within the last decade that the moon is a very compelling and interesting destination. And we're convinced, after extensive study, that in fact it is on the critical path to any other place that we want to go into space. So hopefully after I finish this, you'll at least have some idea about why we think this, if I don't totally convince you. So let me give you the punchline right up front. There are three principal reasons why the moon is an important destination. It's close, it's interesting, and it's useful. By close, it means that it's the most accessible object in space. It's only 3 to 4 days away on typical trajectories. The transport system that you create to go to and from the moon can also access any other point in cislunar space. Cislunar space is the volume of space between Earth and moon. So a lunar-capable transport system can also go to GEO. It can go to the L points, both Earth-Moon and Earth-Sun L points, and even some near-Earth asteroids in terms of energetics and transit time. The moon is interesting in the sense that it retains a unique and relevant record to unraveling the history of all the planets. That's sort of the goal of my discipline. I'm a planetary scientist, which means I'm interested in the origin and evolution of all the planetary bodies in the solar system. Every body has its own unique thing to contribute to that big story. The moon in particular has some particularly unique and important aspects of that. And we cannot ignore what it's telling us about the history and evolution of the solar system and about our own planet and about our sun. And the last item, which I'll go into in a little more detail, is that the moon is useful. It's useful in two senses. It provides material and energy resources that we can use to create new spacefaring capability. But more than that, it acts as a natural testing ground and laboratory to practice doing the kinds of things we're going to be doing as we go further off into the solar system. So let me start off by talking about the proximity of the moon and what its real value is. Now, the moon's only 400,000 kilometers away, and I'd like to put this in terms of light seconds. It's 1.5 light seconds away, which means that I can stand on the Earth and control a machine on the moon with effectively a 3-second time delay, which is not really that difficult. It's very different than the procedures we're currently undergoing on Mars, where the Curiosity rover has to be carefully programmed to do a series of movements. That's radioed up to the rover, and it takes anywhere from 20 to 40 minutes to get to the rover. Then it takes another 20 to 40 minutes for it to get back down till we see what the result was. That's more of a remote teleoperation, whereas on the moon you have nearly instantaneous response. It's much closer to the idea of telepresence. Telepresence is the ability to project a human mind and human reasoning to a remote locality. So in effect, the closeness of the moon allows us to build up a series of assets on the moon, robotic assets, under complete control from the ground, so that we can effectively do real-time operations on the moon from a laboratory on the Earth. The other part about the closeness of the moon that's important is the accessibility of the moon. There's always a launch window to the moon. Unlike the planets, unlike any other planetary destination, like a NEO or any of the terrestrial planets, they have very limited launch windows. And moreover, some of these windows are much more favorable than others. It makes it very difficult to plan and arrange departures for missions because you have to have everything assembled and ready to go at exactly the right moment. And if you miss it, you may have to wait another 24 months in the case of Mars. The moon, on the other hand, can be gone to and accessed virtually at any time. Since it's in orbit around the Earth, we always know exactly where it is. We can always go to the moon at any time we want to. Now, it's true enough that it has a day-night cycle. It rotates on its axis as it rotates around the Earth once every 708 hours. But once an asset is placed on the moon, you will no longer need to see where you're going. You'll be able to zero in and use that as a homing beacon to land anywhere you want to on the moon. So in effect, it acts as a place where you can land and safely go to at any time. Now, another aspect of missions to the moon is that unlike planetary missions or long-duration missions, it's very easy to abort a mission. If you need to come back to Earth immediately or have difficulties with the spacecraft or even difficulties with the crew, you can get back from a lunar trajectory quite easily within a few days. And if you don't think this is important, you should ask the crew of the Apollo 13 mission, who effectively would have been dead if their accident had happened en route to Mars. The other aspect of the closeness of the moon is a lot of people consider the Earth-Moon to be a double planet. The moon orbits the Earth once every 29 days. It has one side we always see, the other side we never see. That unique environment creates some interesting opportunities. For example, from the moon, you can image the entire magnetosphere of the Earth in one view. So you can constantly monitor it, and as the moon goes in and out of the geotail of the Earth, you're actually able to map out all of the radiation bands around the magnetosphere of the Earth. The far side of the moon is permanently shielded from the ionospheric radio noise of the Earth. So it's possible to do experiments there that cannot be done anywhere in space except on the far side of the moon. For example, very low frequency radio astronomy. Astronomers have been very interested in looking at this part of the spectrum, which is largely unknown from the far side because of this permanent shielding. Now let me take a few seconds to outline why the moon is an interesting place. I'm a geologist, and I'm interested in the geological processes that have shaped the planets. These processes include things like volcanism, which is partial melting of the interior and the eruption of magmas onto the surface. It includes things like impact, which is the collision of extraplanetary bodies with the surface of a planet. Both of these are very complicated processes. We understand them in only a very vague sense. We sort of understand that when you have hypervelocity impact, you vaporize a projectile and you basically create an explosive point source release of energy that results in the excavation of a crater. But the details of that, exactly how the crater is excavated, how far down into the crust it excavates, how it modifies over time, and what the products are, how it redistributes the volumes of material it throws out, is largely unknown. And because the moon is a primitive body, it has an enormous number of craters that are available for us to study in detail and to look at and unravel these processes. In addition, the moon has tectonic activity. This is the deformation of the crust, basically the mechanical failure and faulting and folding of rocks, which occurs on the Earth quite a bit, but it also occurs on all the terrestrial planets. We've seen it on Mercury, Venus, Earth, Mars, and Moon. All of these things occur on the moon. These processes are available for study. But more than that, because the moon's an ancient world, and because it has been the companion of the Earth for 4.5 billion years, there's a unique record preserved on the moon that's not preserved anywhere else in the solar system. Effectively, the Earth and Moon are a double planet. So the moon, having no atmosphere and having very little geological activity for the last 3 billion years, has preserved a record of the output of the sun over this period of time. So we can actually look down into the lunar regolith at about 3 or 4 meters and recover the output of the sun 3 billion years ago. The initial attempts to do this with some of the Apollo drill cores showed that the early sun had a different composition of solar wind than the current sun. And that's not been predicted by any astrophysical model of stellar evolution. So we've already found from the lunar record that in fact the sun is more complicated and more difficult to understand than we thought. Another aspect of the record preserved on the moon that can be recovered is the impact flux. As we all know, people often ask me, well, what did we really learn from Apollo? What was the big scientific result? And I always tell them that the most important thing we learned from the Apollo samples was that impact is the most fundamental geological process on all the planets. Now, before Apollo, we sort of knew that there had been impacts on the Earth, but it was considered a freak occurrence. It was a geological oddball. Nobody spent much time looking at it. But then we had to understand the craters of the moon, and so a great deal of effort was put in to understanding the physics and chemistry and the effects of large body impact. Now, very strange, a little side story here. In the 1980s, a father-son team, a guy named Walter Alvarez and his father, Louis Alvarez, who worked on the atomic bomb, in fact, in Los Alamos, were puzzling about something. Walter Alvarez wanted a chronometer to measure the rates of sedimentation of limestones in the Mediterranean basin. And his father suggested he should use the element iridium, because that's quite abundant in chondritic meteorites, but it's very rare in the Earth's crust. So they started measuring iridium in these sediments, and what they found when they got to the boundary layer between the upper tertiary or between the upper Cretaceous and the lower tertiary, they found a huge spike in the amount of iridium. And as they looked at this boundary layer all over the world, there was always an iridium spike. Later in the clay minerals, they found shocked quartz grains. Shock metamorphism only occurs, that's the transformation of minerals in solid state. It only occurs by the passage of extremely large pressures for extremely tiny amounts of time. Megabars for microseconds, we call it. Now, all this was put together along with the mass extinction that we already knew it existed at the end of the Cretaceous, into a story where the end of the Cretaceous was caused by the impact of a giant meteorite. And that meteorite effectively wiped out 90% of fossil families in the geological record. We've since found that these extinctions occur in the geological record on a quasi-regular basis. So the question is there a periodicity of cometary showers that bombards the Earth and basically wipes the fossil record clean? And that's an idea that can't be tested on the Earth because the record is incomplete and fragmentary, but it can be tested on the moon, because on the moon we have the preservation of this record for at least the last 4 billion years. So when the next time someone asks you, what did we get scientifically out of going to the moon, you can respond, we got an entirely new vision of how evolution works and operates on the Earth. And it all came about because we had to understand the mechanics of hypervelocity impact. I want to go one last point, as the moon is a natural laboratory. By this I mean that the environment and conditions on the moon allow us to do experiments and to do studies that otherwise would be very difficult. Now, in terms of, there's two aspects to this. One aspect is it's scientific. Physical and biological sciences both don't have much information about the range of gravity in between the micro and the macro. So we know a lot about microgravity materials and biological science from space research. We know a lot about those two things from terrestrial research. We don't know much about it in the intermediate zone. And that's a critical thing to know if you're going to go to the planets, because virtually all the terrestrial planets other than Earth have lower gravity. So for example, what are the physical and biological processes that interfere or change the rates of operation of these things at fractional gravity? On the moon, the gravity is about 1/6 that of the Earth. So it's an important laboratory to study those effects. But in addition, it's also a place where we can learn how to explore. We went to the moon with Apollo. We know how to examine the rocks and how to do geological field science, but we don't know how to do that with people and machines working together. And that's a key thing. One of the things that will greatly increase our exploratory return is if we're able to allow people to do the things they do well and machines to do the things they do well. That's a skill that we're just now starting to learn using space station, but it's a skill that we'll need to perfect when we go to the planets in the future. So going to the moon and experimenting with human control of teleoperated robots, working in conjunction with field scientists, will allow us to further understand that and to apply it to much greater effect when we go to the other planets. Now, the last reason why we want to go to the moon is because it is useful. It is, in fact, an enabling asset. Now, why is that? It's enabling largely because we now know that the moon contains the material and energy resources necessary to establish spacefaring capability. I've been involved in the last 10 years in a couple of efforts, lunar robotic missions. The first one was in '94, was the Clementine mission, which orbited the moon, and actually did an experiment that suggested that the dark areas near the poles of the moon might contain water ice. That led to a series of missions from both the Europeans, from the Japanese, from the Chinese, and from the Indians to basically send a fleet of spacecraft to the moon and map it in detail with a variety of remote sensing sensors. One of the things I did was to fly a radar experiment. My results are shown up here in this image. This is a picture of a crater near the North Pole of the moon. It shows an enhanced surface backscatter in the interior of the crater, but very little enhanced backscatter outside the crater. The only difference between these two, the inside and the outside of these craters, is the inside is shadowed by the sun, and the outside is not. It's illuminated by the sun. It's extremely cold in these dark areas near the poles. It's in some cases, it's as cold as 25 Kelvin. That is colder than the surface temperature of Pluto. So these extremely cold areas retain volatile elements effectively for the lifetime of the solar system, geologic time. If a water molecule gets into it, it can never get out again. And when we've done the analysis, we find that, in fact, there's probably on the order of about 10 billion metric tons of water ice at each pole. That's a rough estimate. I suspect it's actually more than that because these are the ones we can see. This graph up here shows the result from the L-Cross experiment. In this experiment, we took the upper Centaur stage of the vehicle that sent LRO to the moon, crashed it into a small area near the South Pole. It threw up a plume of water vapor and water ice crystals. And it turned out that we were able to match that with a spectra that's consistent of about 7% weight percent water. Now, that area near Cabeas was an area where my radar doesn't see anything. So in an area where we don't see radar, we have 7 weight percent. In these areas where I do see the high backscatter, it's probably much more than that. So this water is actually in close proximity to lit areas that are near the poles of the moon. Now, we all know that the Earth's spin axis is inclined 24 degrees, so we have seasons that way. When the North Pole's pointed away from the sun, it's winter in the northern hemisphere. 6 months later, the North Pole's pointing toward the sun, so it's summer. The moon's spin axis is normal to the ecliptic. So at the moon, if you were standing at the pole, you would see basically the sun move in a great circle around you once every 708 hours. That's the rotation period of the moon. But because of this sun being near the horizon, some areas are in permanent shadow and some areas are permanently illuminated. So this permanent illumination means that effectively you can deploy solar arrays and generate electrical power constantly. There are very small periods of eclipse that can be handled that are on the order of anywhere from 7 to 30 hours, and you can bridge those by basically using energy storage, a rechargeable fuel cell. So what have we found at the poles of the moon? What we found are areas of water in the form that's most usable. When you find water ice, it's the easiest thing to convert into liquid and gas by the simple expedient of melting. If you have bound water in minerals, for example, asteroids, you have to physically break those chemical bonds, and that takes a lot of energy. What's more, it's hard to process asteroids in zero gravity because most industrial processing requires somehow on gravity, and there's no gravity in space unless you create it. So in fact, even things like convection require gravity. So in effect, the moon is the ideal place to go for these materials and energies. And why is that? Because effectively, you can extract this stuff with minimal amounts of effort, with low-grade technology, and create water, which I contend is the most useful substance you can imagine for spaceflight. Water basically acts as a support for human life. You can drink it and use it for food reconstitution. You can crack it into its components and breathe the oxygen. It's a medium of energy storage. If you have a rechargeable fuel cell, during the daytime you can crack water into its gases and at night recombine them into water to generate electricity. And finally, and most importantly, water in the form of hydrogen and oxygen is the most powerful chemical rocket propellant we know of. So there's not a minor amount here, there's a significant amount. I did a rough calculation for the North Pole. If there's as much water there as I think there is, we have enough water to launch the equivalent of a space shuttle, which takes 735 metric tons of water, hydrogen, water equivalent every day for 2,200 years. So we're not going to run out of this water at any time soon. Now, the interesting thing about this is if we're able to do this, if we're actually able to get at this water, this changes the entire rules of the game of spaceflight. Right now, to launch a rocket from the surface of the Earth, we have a mass fraction, that's the fraction of propellant of the rocket, of about 0.9 or greater. And on the moon, this mass fraction approaches 0.4. So effectively, you actually launch more mass than it takes to get the mass out of the gravity well of the moon. This breaks what my good friend Don Pettit calls the tyranny of the rocket equation. The rocket equation is always going to dictate that to get out of the Earth's gravity well, you're going to be mass and power limited once you get into space. By actually starting to use resources that are already in space, you become mass and power unlimited. So how can we actually approach this? Now, here's where the interesting part comes about the moon's value of accessibility. Because the moon is close, you can actually emplace the assets that you need to begin using these resources robotically. So in effect, I'm doing a shameless plug here. I wrote a paper with a friend of mine, Tony Lavoie, a few years ago, where we actually created an architecture that delivered teleoperated robots to the moon to begin mining the ice at the poles of the moon and actually store that water first for use by the arriving human crews who would come later, and ultimately at a level where we'd export water from the moon. And that water exported will fuel interplanetary missions, it'll fuel missions that go throughout cislunar space. Effectively, it'll create a permanent cislunar space transportation system. And in fact, that's what really we ought to be shooting for in space. We ought to be shooting for space-based assets, Earth independence, and use of resources from off the planet. And in fact, the only way to do that is to start using the resources that are available and in the form we already need them, and all of those occur on the moon. So, I'll just close with a quote from Kraft Erica, is one of my favorites. And I really believe this. I think that in a way, it's almost providential that we have a moon, because the moon that we have is extremely useful, and it will allow us to create a new system of spacefaring system that's permanent, extensible, and affordable. And the way to do this is to send machines back to the moon, let them begin doing the dirty work, including in placing the habitats that people will live in. People will arrive when effectively their living quarters are ready, and we can begin to not only explore the moon as a planet, but explore the other planets of the solar system. Thank you very much. I'll be glad to take any questions.
Well, thank you, Paul. Paul has agreed to take a few questions if we have any. I think we have a limited amount of time. Yes.
Yes, the question was about lava tubes on the moon. They do occur. All the dark areas of the moon that you see, either through the telescope or your naked eye, are basaltic lava flows. And in volcanic terrains on the Earth, a lot of times these flows are emplaced by tubes, which are conduits through which the lava flow is very efficient keeping the heat in, so the lavas can flow great distances. We have found in the LRO images that are being sent down right now by the Lunar Reconnaissance Orbiter several places where there appear to be skylights into these tubes. We'll see a tube, we'll see pit craters along the tube, and in one case, the pit crater looks like it drops down to a floor that looks open on either end. Now, we don't know for sure if this is in fact a tube, but it looks very promising, and it should be investigated. The advantage of tubes, by the way, if you're able to find them, is they're very good places to live, because first you're below the surface of the moon and shielded by many tons of rock, so you've got a nice shielding against cosmic radiations and solar flares. The other advantage is in underground tubes, thermally it's very stable. At the surface of the moon on the equator, it varies, the temperature varies from 100 C to minus 150 C over the course of a day. But in these tubes, it'll be a nice toasty minus 30 C or so.
Yes, Larry.
So would you plan to land on the edge of a crater in order to get both solar radiation from thermal and be able to have access to the water?
That is where we would conduct the initial landings, yes. But effectively, what you really need in the sunlight are the solar arrays, your power station, and then you can recharge your vehicles as you go off to the dark areas to do the mining. Eventually, I would want, for a human-tended outpost, I would want to put it in an area that gets at least quite a bit of excess sunlight, because that way the thermal stresses are not so bad. You've always got some sunlight illuminating it, but we'll probably end up living underground anyway, just for safety's sake.
And commute to work?
Yeah. Well, you commute outside the door.
How would you make the economic case for this? How much would this cost per year? What would be the justification for
Well, in the paper that I referenced that we wrote, which is right there, what we did was to take the runout budget that the Augustine Committee got in 2009, and what they had assumed was $7 billion a year spent on whatever exploration program you had, and we fit under that cap. We have our first productive full-up working level 8 years after the program starts, and 16 years after the program starts, we're producing 150 metric tons of water per year, which is the break-even point. That allows a crew of 4 to go to the moon twice a year for a period of about 8 weeks, and at the same time, you'll use up all the water production. Anything above that is water that can be exported at a profit. So the aggregate cost of our program over the course of 16 years is $88 billion. But for that, we have a completely reusable, in-place transportation system that refuels itself from the moon.
Any other questions? So thank you very much, Paul. It was very interesting, and I think it gave us a goal to shoot for. And the next panel will start probably in a few minutes. We're supposed to get started at 1 o'clock, so if you've finished your lunch, you can start heading back in so we can get started.